Greetings and welcome to another lecture in Introductory Psychology. This one is actually a part 2 in terms of experiments. Part 1 dealt with variables, and if you have not watched that, I would watch that before watching this one, because this builds on that, and you may find yourself a wee bit lost. So when I was talking about variables, I was talking about extraneous variables or confounding variables, and the fact that these are variables that can affect the dependent variable that aren't the independent variable. See, that's why you need to go watch that first video if you haven't, because otherwise what I just said was gibberish. It might have been anyway, but you have a better chance of understanding it if you watch that first video. But at any rate, in order to get rid of those extraneous variables, or better yet, in order to control for them, since it may be impossible to get rid of them entirely, scientists have various ways of designing experiments to do that. And the first, and perhaps the easiest way to do that, is to simply have more than one group in your experiment. Okay? Research almost always has at least two groups, sometimes more, but at least two groups, and the groups tend to fall into one of two categories. The first is called an experimental group. Now, the experimental group receives the independent variable. It is the group that receives the independent variable. Okay? That's why it's called the experimental group, because when you run an experiment, these are kind of the important guys, although do not discount the second group. The second group in many ways is just as important. The second group is called the control group because it's the second group that is used to control for the extraneous variables. Now, the control group is treated exactly the same way as the experimental group, except they do not receive the independent variable. Otherwise, they are treated exactly the same. That way, if it's anything other than the independent variable that is causing a change in these groups, both groups should be affected in the same way. Because both groups are more or less identical, or at least as identical as possible, other than the presence of the independent variable in the experimental group. Therefore, any difference between these groups, when you compare them, any difference must be caused, hopefully, must be caused by the independent variable. If the only difference between the groups is the independent variable, then any difference between the groups must be caused by the independent variable. That's the whole point. You have something to compare it to. If when you give your medication to people who are depressed, if it's actually time passing that makes them better, then both groups will get better at roughly the same rate. If it's the change in the season, again, both groups are going to experience that at roughly the same rate. But if you give one group medication and one group doesn't get medication, and then one group gets better and the other doesn't, that tells you something. It tells you the medication is causing a change. It's causing something to happen. Although remember, you do need to replicate it to make sure it's not just chance that one group changed more than others. I talked about that in the scientific method, which again, if you haven't watched, you may want to go do that. Now, you're going to treat these groups exactly the same, but the whole point is also, though, that they begin pretty much exactly the same. And the way to do that is random assignment. Now, you can't, of course, since we can't clone people, you can't ensure that you have the exact same people with the exact same experiences and so forth in both groups. But what you can do is make sure that both groups are different in a similar way. That both groups, for instance, have equal proportions of older people to younger people, men to women, different racial and ethnic backgrounds, make sure that they are similar. And to do that, you do random assignment, hopefully. Now, this is one of the reasons why doing research, doing an experiment on something like whether smoking causes cancer is so difficult, because the way most people would think to do it is, well, okay, we're going to do a whole bunch of people, and we'll separate the smokers out. We'll put the smokers in this group. We'll put the non-smokers. That's not random assignment. You're starting out with the groups being unequal. You need to start out with the groups being equal. And once they are equal through random assignment, then you inflict the independent variable on one and not the other, and watch and see what happens. Because it's possible that people who smoke have some sort of difference to them that isn't just the smoking. We know that people who smoke are also more likely to drink alcohol. Maybe that's it. Maybe people who smoke are less likely to eat healthy. Maybe they're more likely to do dangerous things. Who knows? Okay? Maybe there's an underlying genetic thing that makes some people more susceptible to not only beginning smoking, but also keeping it up or becoming dependent. We don't know that. And so, therefore, you're not ruling out all the extraneous variables. The only way, well, the best way, I should say, to rule out these extraneous variables is through random assignment. Put everybody together, flip a coin, or the statistical equivalent, divide them up into two groups, and if it's truly random, the groups should be somewhat similar. Like I said, they're going to be different in a similar way. And then you inflict the independent variable on one and not on the other and watch and see what happens. And then, of course, you need to replicate it a few times to make sure what you found was real and so forth. But you need to start out with random assignments, an experimental group, and a control group. But there's still a problem. There are still extraneous variables here. Because if someone gets recruited to be in a study to see whether or not medication helps depression, and they're in a group and they don't get medication, they don't get a pill, they don't get a shot, they don't get anything, that person is going to say to themselves, wait a minute, I'm not getting anything. I must not be going to get better. It's amazing how much the mind affects the body. We've known pretty much forever that vice versa is true. Your body can affect your mind. But by golly, your mind can certainly affect your body as well. And the way to get around that is to run an experiment in certain particular ways. I know some of you are probably thinking, isn't there something like a placebo here? Well, yes. One way to get rid of that whole problem, of that whole I didn't get a pill, I'm not getting a medication, is simple. Give everybody a pill. It's just that some people get a real pill and some people get, well, they used to call them sugar pills, but then they realized that giving sugar to people might not be a good idea, particularly if someone's diabetic. So now it's usually some sort of inert substance. So everybody gets a pill. And therefore the subject does not know whether they have gotten the medication or not. This is something called a single blind experiment. In a single blind experiment, the subject does not know what group they are in. The subject does not know whether they're in the experimental group or the control group, and it does indeed help to control for something called the placebo effect. I have found personally, this may or may not be true for you, but I have found for myself that if I have a headache and I swallow an aspirin or ibuprofen or naproxen or something like that to get rid of the headache, I have often found that within seconds of swallowing that pain reliever, my headache starts to go away. Now, it's possible that it's because the headache is due to dehydration. Boy, the first thing you need to do if you ever have a headache is drink a bunch of water. And therefore, the water I took with taking the pill maybe solved it. But it's more likely that my mind says, "Oh, look, we're taking a pill. We're going to feel better," and your mind immediately starts making you feel better by blocking pain responses or whatever else it does. That's the placebo effect. So what they need to do is make sure that everybody gets a pill. Or, I mean, this could get really complicated. If, for instance, researchers are testing a particular type of surgery, and yes, surgeries are tested like this. If a researcher is trying to test to see whether or not, some sort of brain surgery, it's called psychosurgery. It's not crazy, but it has to do with the brain. And they're going to see, well, maybe there's been some evidence that in people with Parkinson's disease, which causes tremoring, if you go in and you disable part of a brain called the thalamus, it might help reduce the tremoring. Well, if they want to test that, they can't say, okay, we're going to give, half the group an operation and the other half not, because maybe it's not the actual thalamus tampering that is causing the change. Maybe it's the anesthesia, maybe it's the pain reliever afterwards, maybe it's the incision. So what they do to test operations like that is both the experimental group and the control group get an operation, but only the experimental group gets that last little tweak that is theoretically at least the independent variable, the cause. So they go to great lengths to make sure that the subjects don't know what group they're in. But there is still a problem because, as I just gave away in a Freudian slip, we'll learn about that later, who does know what group the subject is in? The researcher. And researchers are human. And even if they try to be as objective as possible, it's not always possible. Now, if a researcher, a scientist, has been working, for instance, on this medication to help depression, and they're certain it's going to work, and they give it to their experimental group and not to the control group, and then later on they're going to interview the both groups to see if they feel better, and the experimental group says, no, actually, I'm not feeling better, the researcher might be likely to go, you're sure? Think about it a while. Are you sure? On the other hand, if someone in the control group says, I'm not feeling better, the researcher is likely to go, okay, not feeling better, fine, let's move on. Remember, human beings see what they expect to see. We'll learn more about this later, probably chapter 10. It's how stereotypes stay alive. We see what we expect to see. We remember what we expect is true. And so the way to get around that is simple. Run something called a double-blind experiment. Because in a double-blind experiment, neither the subject nor the researcher knows what group a particular subject is in. That's why it's double-blind. Single-blind is the subject doesn't know. Double-blind is both the subject and the researcher don't know. Now, yes, somebody knows. This is very easy to do with something like medical research. Because what you do with medical research, if you want to run a double-blind design, is you have all the subjects be given a number. A pharmacist somewhere has a list that says subjects 1 and 6 and 7 and 14 or whatever get this pill, and their other subjects get that pill. And the pills look exactly alike. It's just that one has medication and one doesn't. And then someone else comes in and takes those pills out and maybe gives it to the researcher, who gives it to the subjects. Now, the researcher doesn't know what pill they're giving to what subject. The subject doesn't know what pill they're taking. But then after, weeks of taking the pills or whatever, when the researcher goes back and starts to look at behavior, again, the researcher doesn't know if they're talking to someone who has gotten the medication or someone who hasn't gotten the medication. They only know that after the results have come in, and then they go, okay, let's get the list from the pharmacist. Now, subject 1 reacted this way, they got the pill. Subject 2 reacted this way, they did not get the medication, and so forth and so on. Is this kind of a pain? Of course it is. But it helps control not only for the placebo effect, but also for the experimenter effect. And the experimenter effect, of course, is when the experimenter sees what they expect to see or what they hope to see, or they can try without even knowing it. I'm not talking about scientists going, I'm just going to screw with the data. No, they don't even know they're doing it. Okay? I mean, it's one of those things that is on a level that we are simply not aware of. But this helps control for that. Now, as you can see, between all the variables and all this design stuff, and I have only scratched the surface of how research is done, experiments are kind of, in general, a pain to do. Because you have to control for all those extraneous variables, or you don't have an experiment, or you don't have a good experiment. And it's also why things need to be replicated, because what if there is a mistake made in any one of these steps? There could be a deliberate mistake, there could be an accidental one. Maybe your random assignment wasn't really random. Just by chance, flipping a coin, you could wind up with more of one type in one group than in another, and that could cause a difference. Okay? So yeah, experiments. There's a reason, by the way, that I am a teacher and a professor and not a researcher, because I don't have the temperament to do this. Those that do, however, God bless them, because this is difficult to do. So when someone talks about years and years of research, they're not just sitting on their tush and reading books and eating bonbons while they're doing this. To do good, sound, experimental, scientific research is difficult. It's very difficult. But it's the only way that we know of at this point to be able to accurately reflect the world as it is, and not as we want it to be, or even maybe as it should be.